experiment.
Don't hold that against him.
Don't hold that against him either. Yes, I did experiment with the promise that I could also do theory. A lot of the theory I did initially was on collective models, which is coming back to haunt me and therefore you today. In the past few years, I've moved a lot more into ab initio theory, but tying in terms of discovering some of the origins of collectivity from the nucleon-nucleon interactions, and that is what we will be discussing on Thursday. In terms of an outline for today, right, this is fitting all of geometric models, a little bit over half a century, into a little bit under 3 hours. So this is impossible, and my graduate students assured me beforehand that it would be okay, and that all I needed to give you was sort of an overview so you would know where to look if you needed to do further work on any of these topics. That said, I'll try to go deep enough in a few places at least so you have an idea of what's going on. We'll start discussing sort of a base, well, I'd like to start with a few comments on models in general. We will give an absurdly short introduction to rotors. Then we will discuss basically the quadrupole, basically dynamic quadrupole deformation. Is that large enough for people in the back to actually read? Okay. So we'll be defining the shape variables. Those will be our coordinates, and we'll discuss some of their properties. We'll discuss, and then the Bohr Hamiltonian, which is written in terms of those. There are some limiting cases which we can then consider. Basically, as in most of physics, the cases you can handle are the case of small oscillations, or the case where you have some extra symmetry involved. You've all seen the central force problem in 3 dimensions. There's basically an analog, so-called gamma soft or SO5 invariant problems. And then once you go beyond that, you have to bite the bullet and actually do numerical diagonalization. So we'll be discussing basically the transitional cases. So this will be numerical diagonalization. That's the broad overview. You will be getting a lot of different models in this course. So maybe it's worth stepping back to see, and this is probably, I guess, your sort of first example after the basic introduction to the shell model. You got a survey from Rick of many that you'll be encountering. This may be, maybe the theorist's way of looking at a model is it really has 2 parts. It has a space, so your Hilbert space that you are treating as the proximate Hilbert space of your system, and then a Hamiltonian that's proposed for that Hilbert space. And then you somehow have to find, either analytically or perhaps more likely numerically, with an eigensolver, the solutions. What are those solutions? There is really very little whiteboard space, isn't there? The solutions are, well, you get your eigenvalues. Yeah, I know. If I go off to the side, it will be lost to history. And then you have your eigenvectors, or your wave functions. Then from these, okay, we can circle around. With your eigenvectors, you then put those together with your operators for observables. Which again is a part of your model. What you use as their transition operators in your model. You calculate the matrix elements of these operators, and this gives you a whole bunch of other predictions. So your moments, transition matrix elements, perhaps radii, depending what type of model, and so on and so forth. Right, so the models are, I guess, the shadows where the Platonic form is the nucleus itself. So the basic nucleus we're trying to describe is ultimately some wave function in terms of nucleonic degrees of freedom. So the positions and spins of all the nucleons. We have the Schrodinger equation. We might not know the correct potential to put in it, but we have the basic Schrodinger equation that they obey. So that would be, so we have our Schrodinger equation, sum over particles, kinetic energy of the particle, and then our mutual potential that these particles all feel. So, and then we have our operators for observables, like microscopically, the quadrupole operator would be related to sum over the particles, the charge of the particle, the position of the particle, radius squared times y2. Yeah, we are going to, you will be learning more and more that that's a very hard problem, and we then have these other models, which ideally should somehow touch base with the shell model, be based on the shell model. Now, in today's lecture, we will not be worrying too much, or barely at all, about how the geometric model relates to a shell model. It's basically proposed completely independently. But we will have to come up with analogs of all these ingredients. So in the geometric model, what is our space? What is our Hamiltonian? What are our operators for transitions? Those are the basic questions you ask going into a discussion of this model. So geometric model is actually somewhat broad term. Here, geometry means that we're dealing with the shape of the nucleus, or at least in some abstractified sense, you're dealing with the quadrupole tensor of the nucleus, whether or not you picture the nucleus as actually having a deformed shape. So you have the geometric models. So the space then will be wave functions not of the single particle degrees of freedom, but wave functions of some collective variables. Those might be the coordinates, the parameters that describe quadrupole deformation. That's what we'll deal with today. Then there's octupole deformation, hexadecapole deformation. There may be extra internal degrees of freedom related to the motion of the flow of particles within the nucleus. So there's actually a lot of variety there. Our Hamiltonian will be some sort of effective Schrodinger equation for these coordinates. So it's not the single particle Hamiltonian, but it's something that looks more like the equation for one particle. As we'll see, it will be an equation for one particle in 5 dimensions if we're talking about the Bohr model. Those 5 dimensions are basically the 5 degrees of freedom in quadrupole shape deformation. So we have an effective Schrodinger equation for the collective coordinates. And then, again, our other operators have to be written as some tensors in terms of those collective coordinates. And then you'll see that this, as you can imagine, builds up to a lot of assumptions that go into the model. And then the question is, how well does this model describe what's observed? But then you also have to think, that's okay, but there are lots of degrees of freedom here. Lots of freedom to fit our experiment. Usually we're somewhat data starved. So then you have the question of, all right, we see the shadow, or we see something that looks like a shadow. Is this the actual physics that lies underneath? You'll see some interesting things. You can have many models that produce the same predictions, but with very different physics going into them. So there's the possibility that what you're seeing is the mathematical structure. For instance, you can have, you'll see the interacting boson model a lot this week, which has an SU3 limit, which looks very much like the collective rotor in the geometric model. When you look at the predictions, it looks very much like the so-called Elliott SU3 model of the shell model. And you have the question, okay, you see very similar predictions coming from possibly very different physics. You may be recognizing the symmetries. You may have gotten the symmetries right, and you still have to ask, does that mean the underlying physics is right? And I don't have an answer to that. That's sort of an open-ended question. It's something to keep in mind in general with models. Okay, so what is the sketch going to be here? We're going to start as more or less a warm-up by looking at something that the idealized rotor. That's a system where what is our space? Its functions actually just of the degrees of freedom of something that's rotating are the Euler angles. After that warm-up, we are going to go to the Bohr model, which is what we'll focus on in some generalized form. And that has the quadrupole moment components. We'll define this a little bit better as its coordinates. So the space is wave functions on those coordinates, which are basically square integral functions in 5 dimensions. That's the problem we will be dealing with. And then, as I mentioned, there are further extensions beyond that, which you can spend the rest of your life reading up on if you're ever curious to. Okay, so, maybe would it make more sense to raise the screen? Oh, I should say, I'm trying to do this mostly on the whiteboard, at least for the first part, on the assumption that if you start seeing things just on transparency as they start whizzing by and your eyes start glazing over, that does mean, though, I realize some of what we're using in the exercises is things I'll be writing on the board, and I'm noticing that about half of you are taking notes and about half aren't. You might want to, I don't know, maybe I should make a loud noise or something every time there's an equation you'll actually need, or maybe you should just make sure you have a friend who's taking notes or something along those lines. I do find, in general, that actually writing something down as you're hearing it does force you to think about it a little bit more and can make things stick better, so that was also part of my motivation here. But, all right, I will just keep trying to...
You can raise the board.
Yeah. How do I do that?
Let an expert do it. That only took 4 of us.
Oh, that's okay. Yeah, well, because if it goes off, then it takes a while to warm up. Yeah, I'll wait. I'm just creating trouble, aren't I? Okay, so a discussion of the rotor, with apologies to everyone who's ever worked on rotors. Okay. So if you have a rotor in 3 dimensions, the natural rotational Hamiltonian would involve some moments of inertia times the intrinsic. So the thing is, you have the shape that's tumbling over itself. You have to look at its intrinsic frame to find the moment of inertia around each of its intrinsic axes. So, okay, the idea being we have some laboratory frame with x, y, and z axes, and then some intrinsic frame with, let's call them 1, 2, and 3 axes. No, we should make the z-axis along the end here. So let's say 1, 2, and 3 axes, and the coordinates are the Euler angles that rotate one set of axes into the other. Now, there are components of the angular momentum taken with respect to the laboratory axes. Then there are also coordinate components of angular momentum taken around the intrinsic axes, which we will, in these lecture notes I was going crazy, every author has a different notation for them. Why don't we use a prime for the intrinsic components? For the next few minutes at least. Now, let's write this out in full. There will be 3 terms here. How many have done some form of derivation like this at some point before in some class, just out of curiosity? Since if you have, you'll have gotten an infinitely better version than what I will compress into the next 2 or 3 minutes, but at least this serves as a starting point. Okay, that's curious to see. I should point out there are good reviews on a lot of this material. Okay, there are the textbooks. The classic, of course, there are the Bohren-Mogelson textbooks, Eisenberg and Greiner. There are 2 textbooks by David Rowe, an old one and a new one, both of which are available through World Scientific, which give a much more complete introduction to a lot of this material. Okay, so what are we going to do with this Hamiltonian will be our question. Can we make any sense out of it? And there are a couple of cases that will be significant. The first is if we have an axially symmetric shape. What can we learn? When we talk about rotors in nuclear physics, very often we're actually thinking about axially symmetric rotors. If we have an axially symmetric rotor, that means that the moment of inertia around 2 of the axes, say the 2 axes coming out at the equator, will be the same. Now on the flip side, so we've written a Hamiltonian here. We're looking for our wave functions. Now those wave functions can be written in terms of states that have good not only L, but also K and M. L and M are familiar. We have a problem that's invariant under rotations in the laboratory. If space is isotropic, so we'd expect to be able to find wave functions that have definite angular momentum and definite projection along the z-axis. The thing is that there also exist functions that, in addition to those 2 properties, have a definite projection along the intrinsic z-axis as well. So let me maybe draw that fresh. Here is our nucleus. Here is our z-axis in space. Here is the z-axis defined by what we call the 3-axis defined by the intrinsic frame of the nucleus. Now, this is where notation gets really fun. If this is our angular momentum, for the simple through we're doing, it's easiest to call that L. So I should probably give you a caveat. There are distinctions between the meanings of L, I, J for the angular momentum. Probably some of you who know more about this will be groaning by using L here. You can look it all up if you're curious. The basic issue is whatever the total angular momentum is here, this has to do with Luzia. There are lots of subtleties going on. Okay, you have a top that's tumbling over itself. That has some angular momentum due to its rotation. But that's assuming there's no internal structure. As soon as you start getting to the nuclear physics applications, you realize that this top is actually a nucleus made up out of nucleons, and if you're looking at the tumbling of the overall shape, you also have to ask, well, what about the motion of the nucleons inside? And that can contribute non-collective. So the overall motion gives a collective angular momentum. There's also a non-collective contribution due to the motion of the particles inside. I don't dare go into all those details. But the basic issue, simplifying quite a lot, we have that there's some projection, which is called K, along the 3-axis. So here's another caveat, K versus omega. You can have fun looking this all up at some point. you have and then m along the z-axis, and L simultaneously as good quantum numbers. And how can we build these wave functions with those definite quantum numbers? That comes out of angular momentum theory. These wave functions have, let's call them phi, L. They are basically Wigner's D functions, which you've seen in another context when you first learned angular momentum as the functions which give the transformation matrix between the rotated angular momentum. So angular momentum eigenstates when you do, then they undergo rotation. So they're functions of the Euler angles, which are exactly our degrees of freedom. So by omega, we mean the Euler angles, which choose a random set of 3 letters to represent them. Let's not do that. Okay, and then some normalization factor. There are some subtleties depending whether or not the k quantum number is 0. And then it turns out there's one important symmetry which we don't dare ignore, which is basically a top like this is not only symmetric around its equator, but also if you rotate the whole thing 180 degrees, tumble it over, you also have symmetry. That would flip the projection k to minus k, so we need a symmetrized wave function, which, again, without proving the details, involves some phase factor between the d function with the subscript k and the d function with the subscript minus k. Okay, so this is our rotor wave function. Or we can hope to build our solution out of wave functions like this. For the symmetric top, it turns out this is the wave function. So an axially symmetric top and we'll see a lot of this recurring then as a basis for what we do with the geometric model. So that here we have an axially symmetric top. That means that 2 of the moments of inertia are equal. Let's call them J. We still have a third one, the one around the 3-axis here, which is different. And we can rewrite the Hamiltonian, if we are clever enough with algebra, as L squared over J plus some combination of these moments of inertia times the 3-component of the angular momentum squared. So we say, wonderful, we already have eigenfunctions of L and of the 3rd component of the angular momentum. And so we know the solutions for this Hamiltonian. They're what we just found. And the energies then would be h bar squared over 2, the eigenvalue of the L squared operator, which is LL plus 1, divided by its constant there, and then this other combination of moments of inertia times k squared. We'll see this as the basis then for rotors in the geometric models, one of the limiting cases where this will no longer be strictly true, but will be the approximate starting point. Questions so far? Okay, we're just getting started on this tool. I'll be signing autographs later too. Okay, so we have, so there's one more case which is going to be used in the exercises, or at least you'll get to actually do a numerical code calculation within the exercises. Again, because of time, we're not going to fill in all the details, but I'll give you an idea of where some of this comes from. You saw in Rick's lecture one of Rick's favorite models, which therefore, since I was a student, became one of my favorite models, which is the, what you call it is, it goes by lots of names, asymmetric rotor model, Davidov model, Meyer-Turpin model, probably some other people have taken credit for it too. So the idea is what happens if you have three completely different moments of inertia, which would be what you would have in general if you had a triaxially deformed shape. I should comment that this also all overlaps a lot with molecular physics. What do molecular physicists deal with? Molecules that are undergoing rotations and have various moments of inertia. So if you, these ideas have been around in a lot of contexts. So what if we don't have this simple case? We can still use these functions as the basis for our solution, but that means we need to figure out the matrix elements of our Hamiltonian operator between these basis functions, so that we then have a matrix to diagonalize to get our eigensolutions. So we have to group these not very convenient operators. All of you know by now that the Cartesian components of the angular momentum are all but useless things. Normally we're dealing with spherical tensors, you know the wonderful thing you have with angular momentum. Take linear combinations to get the L plus and L minus operators. Those are operators which you can then actually calculate matrix elements of. So we would need to regroup the components of the terms in our Hamiltonian here to get something that we can actually work with. Our basis functions have definite intrinsic projection K, so that is where that's what's going to motivate our reorganization. And I'm just going to write it down rather than going too much through predicting the best way of doing it. Again, we're not actually grinding through all the algebra right now. But the idea is we're going to treat the L3 prime operator a little bit specially. Right, the angular momentum squared in the, no, I didn't want to write that. Oh, that was L2 prime, sorry. So think back to angular any vector. The total length squared is the x squared plus y squared plus z squared parts. If you subtract all, so if you know the total angular momentum squared and you know the z squared, you can subtract that off to get the x squared plus the y squared. So anything that's the x component squared plus the y component squared, we can handle pretty well. So that term we'll be happy with. This is in the 1-2 plane. Squared projection in the 1-2 plane. We can break this then, we can break out another term which involves the difference of those squares. This might be a little bit less obvious why it's useful, but it turns out, remember, difference of squares is basically the sum of two things times the difference of two things. Well, the sum of these two operators is the raising operator, the difference is the lowering operator. That's sort of fudging what's going on. But basically this can be rewritten in terms of the ladder operators. And then we will have the z projection squared. So again, this is still not very pretty. Let us rewrite this into things that are a little bit more closely related to matrix elements. Since I told you all that you should furiously take notes, I should probably give you the disclaimer that you'll be given in a notebook the final result that you need on this, so don't blame me for all the writer's cramp afterwards completely. But if you do want to take notes, that probably is helpful, but it's not absolutely necessary. That should be an L squared. It would help if I actually wrote the right things on the board too. And then this, again, there are some details of the algebra which you would have to check on your own. Is written in terms of the ladder operators, and then we still have the third component. And, okay, we now know how each of these parts act on our basis. squared acting on the d function. Our basis is written in terms of d functions, so all we have to worry about is the d function is L plus 1 times the d function. So wait, we're taking the easy ones first. The third intrinsic component acting on our d function pulls out k times the d function. Then there are these intrinsic raising and lowering operators, which I direct you towards the appendix of a good textbook if you ever want to deal with them. I just want to flag for you that they look a little bit scary. How do we deal with operators that are angular momentum operators with this mysterious prime sitting on them? But there are relations very much like for the regular components with some subtle differences. Like it turns out that the thing that looks for all the world like it should be a raising operator, the plus linear combination, turns out to actually lower the quantum number. And you would again want to look up all these relations before actually applying them. So plus operator lowers. There's a similar relation for the L minus operator, which I'm not going to write down. But in the end, let's step back. As often in these theory problems, there's a lot of detailed algebra, but you need to step back and see the basic ingredients. We have a space. Yes, we have a basis for our space. By hook or by crook, we figure out how the Hamiltonian acts as an operator. We've gotten our matrix elements, and the rest is diagonalization. So we have a model. Now there's one thing missing, which is what are these moments of inertia? And when we get to our geometry, so those might be something that come out of microscopy, or in our geometric models, we will see when we introduce Bohr variables very shortly. So in the Bohr model, there is a specific expression for the moment of inertia. Right, the Bohr model is describing the nucleus as having a quadrupole deformed. It's basically ellipsoidal shape, and you can actually figure out what these moments of inertia are, and it will be expressed in terms of the Bohr beta variable. I know there's slight nonlinearity, we haven't defined it, but basically I can rest on the assumption that Rick Caston introduced you to all of nuclear physics last week, so any symbol I throw on the board you probably already know. Okay, but the short version is there'll be some mass parameter, there'll be beta squared describing how stretched the ellipsoid is, and then some trig function of basically the asymmetry of the axes. We'll define all this carefully in a moment. So I should probably stop and ask all sorts of things like which of the symbols on the board would you most likely to ask what language's alphabet it's out of and things like that. Yes?
So there's some confusion. So
Yeah.
it's 4 times and it's 2 same letters.
The perfect example, yes, okay. This is, and again, this will make this is slightly circular. This is the letter B from the Roman alphabet.
Yeah.
Okay. This is the letter, this is not a double S from the German alphabet. This is the Greek beta. Yes. And so that is the perfect segue into defining what those symbols mean. Okay. Actually, any other questions? I do apologize. This is the type of introduction which would absolutely drive me nuts as a student. But since the organizers did not give us a week on geometric models, we're sort of stuck with this. Okay.
Sorry. So fine.
Yeah.
You so L plus act on the basis
Yes.
D K the projection decrease.
Yes.
Fine use this convention. So it's somewhat confusing.
As opposed to, wait, there's the L plus operator which would act on the M, and then the L plus prime which acts on the K. Is that the question?
I think he's asking why the plus goes with decreasing K.
Oh, is that the question? Oh, yeah, because the plus comes from, so the plus, right, there are two choices here. It turns out, so if the plus is so L plus, just like we have L, Yeah, you're not the only person that just drives nuts, rest assured. Okay, so we have L plus or minus is, what is it, minus plus, no, I'm doing the spherical components, sorry. That's Lx plus or minus Ly. So here, the choice, and again, people could have made either choice, but this is the one which stuck. L prime plus or minus is, naturally enough, L prime plus or minus x plus or minus deck. L prime x plus or minus L prime y. So it's the sign that goes between those components. It's just our unfortunate luck that that combination happens to lower the intrinsic projection instead of raising it. I do not pretend to have derived that. Yeah?
I was taking notes when you said something about the Bohr model.
Yeah?
So is it the inertia moment, inertia?
Yes, these are the, so these J's are the moments of inertia, and sorry, that is supposed to be a K, and again, this is, so the K is running over the three axes here. Anything else?
Oh, so so L prime x is the intrinsic moment projection in the lap frame or lap axis x. Lap axis x.
So I should, yeah, so we're, notation is so yeah, this should actually be O1 and O2.
Yeah,
Although,
that
yeah,
makes more sense.
it makes more sense. Unfortunately, I mean, in reality, it should just be the prime that distinguishes, because as you all know, once you get past a certain point, calling the axes x, y, and z is ridiculously tedious, since you can't sum over x, y, and z. It makes ultimately a lot more sense to use 1, 2, and 3 also for the entrance, for the lab axes, and just worry about whether you have a prime or not. So I am, even in assembling this lecture, there are umpteen different conventions, and say about the lecture's supposed to be in French, right? Okay, so speaking of different conventions,
So could you remind what is D?
yes, okay, so the D function, and this is going to drive us nuts also, this is in Bohr-Modelson's convention, which, as luck would have it, is, so Bohr and Modelson developed all this collective model stuff, and they chose the opposite convention of what became the standard convention with everyone else. Their D function is the complex conjugate of the D function used by the rest of the world. Okay, so the D function is, this will be a test of my, how well I remember introductory quantum mechanics. Sakurai, okay. So the basic, let's see, the D function is a fancy name for, let me erase some of this. So everything I write today will be correct, modulo random phase factors and normalization factors, because there is no standardization. Okay, so the idea is you have some angular momentum eigenstate, Lm. Now what happens if you rotate everything by some Euler angles? So you have the rotation operator by some Euler angles acting on that state. So this will give you some new state, Lm okay, let's just call that our new state. Now let's not give it a new name. So what does that do? Rotating a state will not change its angular momentum, but it will give us some linear combination of the other m states. So some linear combination of m prime, Lm prime. The D function gives us those coefficients. This is probably easier to write and less likely to get it wrong if I write it as, so let's expand this out. This can be written as sum over m prime what we have to do, we have to insert a resolution of the identity, so we have Lm prime, rotation matrix, or rotation operator, Lm. These are some numbers, and these are, in the usual convention I believe, these are the D functions, D, L, M prime, M of omega. So the argument is the angle, the Euler angles of rotation, and then these indices are the angular momentum involved, and then the projection quantum numbers. That's how it's introduced, and then it's this extra bonus, basically, that those functions turn out to have all these special properties as eigenfunctions of the angular momentum operators. Yes?
So I guess I'm a little confused as to why you keep referring to this matrix as, like, the eigenvectors of this matrix form these functions you're talking about? Or?
The entries of the matrix are these functions. So these two completely different contexts for the use. These are, the Wigner D functions they're defined as matrix elements, but those matrix elements depend on the rotation angles, so we can think of them as functions of the rotation angles. Now we put on a different hat, our rotor hat here, and we say, oh, a rotor has as its coordinates the Euler angles, and we need some function of the Euler angles as our wave function. It turns out that these serve at least as a basis, and it turns out they're actually the eigenfunctions in the axially symmetric case.
Mark,
Yes?
just the typo. I
Only
think the
one?
I is missing in front of Li.
Oh, yeah, thank you, thank you. Any other fractions? All right. Okay. So, let's see how we're doing. Okay. So let us introduce quadrupole coordinates. At some point I will, so we want to figure out how to turn the projector back on so it is ready. Okay, while we're doing that. Well, I'll start writing on the board while we're waiting for that.
Since now you introduce the D functions, don't you think we should like see their symmetries?
In the sense of...
In the sense that we were talking a lot about gamma and beta band, and then we were referring to them like K0 band or...
Oh, yeah, so there will be...
and I think this comes from the symmetries of the D function somehow.
It's...
Why do we have even spins or even spins?
So there is one, when you have a k equals 0 band, if you look at the thing that I erased here just a moment ago, you will notice that, yeah, that's a fun point. For the case where k equals 0, dl km plus minus, our wave function dl km plus minus to dl minus km becomes, notice, k versus minus 0 and minus 0 are very close in floating point arithmetic. Minus L dl 0 m. So indeed, this is 1 plus minus to the L dl 0 m. So we will get, yeah, this will basically, for odd spins, this will cancel out. Now, actually, you can actually have all odd spins in the k equals 0 band. There's a little bit more of a subtlety, which will actually, I guess, be in my lecture notes on Thursday. We'll skip that. Okay. Let us go on then. So the quadrupole coordinates. So look, what's the basic idea? so here we have a pretty picture, exactly the type of thing we were talking about just now. For a rotor, we will have various bands. There will be some intrinsic structure which doesn't show up in this basic rotational, just this ideal top here. We weren't talking about the intrinsic structure except indirectly through the K quantum number. So we will have these bands with different intrinsic structure which gives us different K quantum numbers. There are various patterns of transition strengths, the so-called oligo rules, which Rick introduced to you, which come basically out of the tensor character. It comes out of the fact that you have these D functions that control different states of different angular momentum share the same intrinsic structure but have different D functions going with them. Yes?
So in this case, since we're not working
Yeah.
in harmonic oscillator, but this new Hamiltonian, what is little n?
So this is, we're doing things again completely out of, we will get to that later today. This is sort of, this is a bit of a preview. Yeah, we will get to defining these little n's.
Even in the spherical, is this little n?
The little, yes, we will.
Okay.
I will probably call it big N, but we can use our imagination. Okay, so the idea is if you have a quadrupole deformed shape, you can expand the radius as a function of angle out from the origin. So these are just good old angles theta and phi now, they're not Euler angles we're talking about. Spherical harmonic times some coefficient. So we have 5 of these. And let's not bother turning the screen on and off so we can turn the lights.
I think the first one.
Okay. It's L1, so that's the intrinsic x-axis, whereas the L2 button would be for the lights on intrinsic y-axis. It's only funny if you're actually looking at the control panel. Okay. So, part of the reason for focusing on the next discussion is the normal proper response is to panic when you see complex functions times complex coefficients describing a real radius, and then wondering what it means to write a Schrodinger equation in terms of complex variables. The good news is that this is all real variables in disguise. Okay, so we have that expression there. So r theta phi, maybe I should write it down here, just those first few terms. R naught 1 plus sum from mu equals, I think I had an m there, sorry, minus 2 to 2, alpha 2 mu, y2 mu. Yeah, different conventions again, sorry. Y2 mu star theta phi. Okay, so for this to be real, the radius here has to be real. The thing to realize is that we're adding linear combinations, like the -2 component and the +2 component. Those spherical harmonics are related to each other very simply. It's the same Legendre polynomial, and it's just that you flipped the ag. Let me rewrite that cleanly. I-U phi. So these come in complex conjugate pairs. If we add them up with properly complex conjugate coefficients, we'll get real linear combinations. You can check the algebra yourself, but the condition will basically be that alpha 2 mu star will have to equal alpha 2 minus mu with a phase minus to the mu. Yes?
So when we're describing some sort of deformed shape,
Yeah.
why don't we include the L equals 1 spherical harmonics?
So you could, so let's see, what the L equals, we can start even earlier. There's the L equals 0
Isn't that
spherical harmonic.
dipole deformation in the
Dipole.
state?
Yes.
That's
So
something QCD somewhere. Has to do with
Well, or it actually has to do with even much more elementary translational invariance, center of mass motion. So if you, let's sketch out what happens. Take a sphere, and if you add on a constant to the radius, so that's the L equals 0 spherical harmonic, that will be a change in the volume. So that is basically describing breathing modes of a nucleus, or else that can be used to conserve volume when you add on other spherical harmonics that might change the volume otherwise. So this we're leaving out when we're just looking at deformation. This is a change in size. You can sort of hand wave it away by talking about incompressible fluids. Now here, L equals 1, what does a dipole do? So this is our basic sphere. Now, if you add on, the wonderful thing about dipole is that it's positive along in one direction and negative in the other. So along the North Pole, we'd be adding a positive amount. Along the South Pole, I know that doesn't correspond to the usual map directions, but I'm picturing the z-axis this way. I don't know why I did that. You have a negative amount. So you basically, to leading order, you've just shifted the nucleus, translating. That's a perfectly good thing to do, except we're interested in the dynamics of the nucleus in its center of mass frame. So dipoles do become important if you're looking at the distributions of protons and neutrons separately, where then it's perfectly meaningful to shift the protons to one side, the neutrons to the other side, and get oscillations of them relative to each other. But for a uniformly homogeneous fluid, quadrupole is the first one that comes in. And then you can look at higher multipoles, octupoles, important, hexadecapole sometimes is too. Okay. So, this means, though, that even though conventionally things are written most of the time in terms of these complex coefficients, let's look at what happens if we write these. These give us a couple of conditions, in fact. It gives us the condition that for the mu equals 0 component to be equal to its own complex conjugate means that it is real. So we can just write it as a single real number. For the plus or minus 1 components, though, we will have that they will be plus or minus times, I'm going to throw in a 1 over square root of 2, not just for fun, it makes things work out nicely later. There's actually a significance to it, A1 plus or minus IB1, where these again are real. And then we have alpha 2 plus or minus 2 will be 1 over root 2, A2 plus or minus IB2. So even 5 complex numbers with these 3 effectively complex conjugation constraints leave us with 5 real variables. So we can write this problem actually in terms of the real coordinates. I was so happy when I discovered this, that this wasn't all as strange as it seemed. We're basically working in, you can read this clearly, can't you? Okay, so we have these 5 coordinates. In fact, sometimes they're just referred to as x1 through 5, or x plus 2 through minus 2. Notice that they come in natural pairs. That's the reason for this plus or minus notation. And the reason I stress this is there are a lot of things that will seem a little bit mysterious, like we heard about gamma softness. Independence has all these special properties. It's described by an SO5 symmetry. Well, we'll get to this again later today. SO5 is the group of special orthogonal matrices in 5 dimensions, which means rotation matrices in 5 dimensions. So SO5 is just symmetry under a rotation in the 5-dimensional space of these coordinates. So it's actually starts to look like slightly more familiar things. Okay, we are dealing with a mechanical model. So in addition to coordinates, we need momenta to write our Schrodinger equation kinetic energy in terms of. There are again a bunch of tedious details involving signs and complex conjugation. So take everything I write with a slight grain of salt, and there's a wonderful article by Prochniak and Rosinski, which someone who speaks Polish should correct my pronunciation on, which covers a lot of this, plus the various textbooks I mentioned. The basic thing is we basically have derivatives with respect to our alpha coordinates, partial derivatives being our momenta. And derivatives with respect to complex numbers look a little bit scary, but you remember those can be rewritten in terms of derivatives of the real and imaginary parts. And it should include some disclaimers like actually it's the dagger of this operator is the conjugate. But momentum, but let's gloss over a lot of these details. So what are we after? So the basic thing is we have our, okay, so this is the form you'll usually see things in, which means we have to go a little bit further. We have to take these alphas and write them yes.
There's a stick if you want to point on top of the podium.
Okay, I also have a laser pointer. The thing much more important than a stick would be a third hand. Yeah, I won't try. I will point this way. Okay, thank you. Thank you for thinking. Okay, so yeah, so we need to get from these alphas into what will be, in some ways, more natural coordinates, Euler angles for the ellipsoidal shape, and these other parameters, beta and gamma. So let us step back and derive what's going on. Everything we've written so far is just written in terms of the laboratory coordinates, theta and phi. Nothing yet involving the intrinsic frame. But you can ask what happens if you do a change of coordinates, a change of axes, to the intrinsic frame. And I probably should have used prime for these, but I was switching to, okay, I'll try to do this on the fly. Let's call these, use primed, and there'll be an A instead of an alpha just for good measure, to describe the intrinsic, right? Once you go to the intrinsic frame, we have those axes set up. This shape is still quadrupole deformed. We can still write expansion coefficients for its surface shape. And those will transform, since the spherical harmonics transform as a tensor, those will transform as, and whether you include a complex conjugate here depends what convention you're using, d mu nu of omega alpha to mu. So here we really are using the d function in its original sense, the transformation coefficients when you take a tensor and rotate it. So this is going from the lab frame to the intrinsic frame. So again, as a reminder, we have our lab frame, we have our intrinsic frame, and they're related by some Euler angles.
So A prime is from intrinsic.
A prime of intrinsic frame. I will try to standardize on that. Wish me luck. Okay. So this implicitly defines actually what those Euler angles must be. Suppose somebody gives us the alphas. We can ask what Euler angles will then give us A's, which look like A's should be in the intrinsic frame. There are a couple of things going on in the intrinsic frame. if you look at what the different spherical harmonics do, the y0 and y2s will give you things that are nicely aligned along the axes. It's the y plus or minus 1s that will tend to give you a shape with its symmetry axis pointing out in some random direction. So basically, the conditions will be that A2 plus or minus 1 prime, so in the intrinsic frame, will have to vanish. That will keep our axes, our shape aligned along the axes. And also, it turns out that you need A2 plus or minus 2 being real. So that means in the intrinsic frame, we have, let's go back to our way of writing this in terms of components. We always just have a real part for A2, 0. Now we'll have A2 plus or minus 1 intrinsic will be 0. And then A2 plus or minus 2 intrinsic, since that's real, will be a 1 over root 2 A2. There's some issues with square roots of 2, but this is the standard. I think I slightly contradicted the earlier definition, but this is the standard at this point. Okay, so we can look backwards and say, this is how the shape would be described in an intrinsic frame. So we have these numbers are very important numbers. They describe the shape of the nucleus itself. How stretched it out is along its own natural intrinsic axes. But then we can go back and write our original coefficients, these alphas, in terms of these A primes by inverting the rotation. Rotate backwards by the Euler angles, while doing the negative rotation means taking this is a unitary transformation, so we basically have to take the transpose conjugate. So what do we get? We get that so rotating back, we have that these alpha 2 mu's are sum over nu's d2 nu mu. All right, we're setting up the formalism here. Very soon we will get to the point where we write Hamiltonians in terms of these and call it a day and start solving things.
So,
yes.
a question, so,
Yeah.
just geometrically, 1 A2 plus minus 1, what is that thing?
So we will, and in fact we'll get to that in just a moment. Oh, which?
Because I just cannot understand why is it 0.
Oh, let me think for a moment. So we have to look back in terms of the Legendre polynomials, which I'm not going to be able to sketch off the top of my head yet. Oh, there's a fixed time for the break. Okay, sounds good. Okay, we'll break in 10 minutes. If someone would be inclined to look up Legendre polynomials, let's see, we could Google Legendre polynomials.
If it's too
Yes.
lengthy, maybe we can skip it for later.
Yeah, I think the rough idea is, don't hold me to this, but I think those Legendre polynomials do something like that, which would give us stretching on, not along the axes. Okay.
Okay.
Yeah. It's the D, yeah, this goes like the D orbitals, and there are several different D orbitals, and there are one with lobes to the sides, I think. I don't know, ask a chemist. Okay, so we have yes, so rotating backwards, we have A2 nu primes there, so we end up with A naught d2 0 mu omega plus 1 over root 2 A2 d2 mu omega plus d2 minus 2 mu of omega. Right? We have 5 terms here, 2 of which vanish as we just said, 2 of which are closely related to each other. Still is not terribly illuminating. The convention then is to rewrite these in polar coordinates. Right, we have 2 numbers, A0 and A2, 2 real numbers. We are always allowed to write those in polar coordinates by defining a radius and an angle. Those are the Bohr variables. So Bohr's polar coordinates. A naught equals beta cosine gamma, A2 is beta sine gamma, which gives us, when we put those in, the classic expression for the quadruple coordinates in terms of these variables. The beta here is the radius in 5 dimensions. So that tells us something about what it means. So let's think about this. Beta squared, you'll get to fill in the details of this in the exercises, is A naught squared plus A2 squared. That's just our definition here. But this is actually independent of the system that we use. So this is one other way of looking at this, is that this is the sum over in the intrinsic frame, sum over the xi coordinates. And that is a rotational scalar, so it doesn't matter what frame we actually look at it in. So it's the sum over the alpha 2 mu starred alpha 2 mu. You can check that sum over mu in any frame. So it basically describes, if you increase beta but keeping gamma constant, you're basically multiplying all your deformation coordinates by a constant, so you end up stretching your shape out, which if we all had beautiful, perfect 3D perception, this would look like. You can sort of use your imagination, see us going from a sphere to a stretched shape to a more stretched
Alpha
shape.
to m star times alpha to m?
To m, yes, or mu.
It's alpha or it's a?
Sorry, that was, it's either actually, since this is rotational, so to fill in a step there, it would actually be sum over mu, a prime to mu star, a to mu, but since it's a scalar, you can look at that in any, prime, you can look at that in any frame, so it's alpha to mu star, alpha to mu. That's beta. Gamma then gives us the ratios of the component that, the 2, 0, the y20 component, which actually, why don't we do that? No, it's I think, so you have the Legendre polynomial y20, or the spherical polynomial y20, stretches out the ends. And then you have y2 plus or minus 2 will, I don't quite know how to draw this, they will, if you look at the equator, stretch out to one side and the other. So they basically give us, sorry, that's a horrible drawing, but they give us the difference between a prolate shape, an oblate shape, or a traxial shape in between. All right, so there's actually, this sounds a bit scary though still, in that it seems like in order to do anything that has to do with the beta and gamma coordinates, we'd have to transform to the intrinsic frame, but we will find that there are some linear combinations, you'll again check this on the exercises, which will show up, which are, so we've seen here though already that basically some simple combination of the alphas gives us beta squared. In fact, as you will see, these will be ingredients that will write our Hamiltonians in terms of that. We have 4 more minutes, okay. We have alpha cross alpha coupled to 0, for instance, gives us, oh, you'll derive this in next. No, let's do it. I won't keep it a surprise. 1 over root 5 beta squared, alpha cross alpha to 0 is some coefficient times beta cubed cosine 3 gamma. So the shape of the nucleus is hiding in these properties. Yes?
Cross?
Oh, okay. I'm not sure then how much of, have you been introduced to spherical tensor coupled products of operators? So here's the short version. Some people write it with a cross and some don't. So help me out, I should remember from the notes. Has a spherical tensor operator been defined?
Not really, but we did angular momentum properly. So
Okay, so for states you have, all right. So, okay, I have a general recommendation, which will be, what my students have found to be a really good introduction to spherical tensor coupling is Suhonen from nucleons to nucleus. Yeah, it's by Springer, which means there's a very good chance that you can download it for free under your library subscription. You may be able to download it for free from Gneal, I don't know. Chapter 1 and 2 provides all those wonderful identities which very few people have collected everywhere in one place and spells out a lot of the details here. But basically, yes.
Yeah, maybe you can write out the first of them, of the alpha cross alpha coupled to Z.
Yes, so let us do this. So how this works, yeah. So if you have two spherical tensor operators, which I know we've just bypassed defining what a spherical tensor operator is one that carries a definite angular momentum. We've bypassed what that means. Wait, but you have the Wigner-Eckhart theorem. You have spherical tensor operators. Okay. That doesn't mean I know that you have a good feeling for them, but you'll have that after reading this. So T cross mu. So let us do this. Now let's do this like a more coherent notation. Suppose we have two operators A. A spherical tensor has both angular momentum to it, that's also called its multipolarity, and an angular momentum projection. This is defined in terms of its commutators with the angular momentum generators, which I think were in your notes. Okay. So suppose we have two operators. Suppose we also have an operator B, which is also a spherical tensor. Just to keep this easy to remember, let's call its angular momentum little b, and its projection beta. So it turns out that you'll get a spherical tensor operator again, one that obeys the proper commutation relations with the angular momentum generators, if you combine these in a certain way. So your new tensor, C, angular momentum C, projection gamma, you can get from these two by combining their components in a certain way, which is denoted by taking this angular momentum combination C, coefficient projection gamma, doing this exactly as if A and B were states, multiplying them together and multiplying by Clebsch-Gordon coefficients. So this is defined as sum over projections, alpha and beta, Clebsch-Gordon coefficient, A, alpha, B, beta. Okay, there are umpteen different notations for Clebsch-Gordon coefficients. This probably, I'm using sort of a group theory way, which, okay, is my peculiarity. This you've probably also seen written as A, alpha, B, beta, C, gamma. A, alpha here, B, beta. Oops. And notice, even though I've written this as a double sum, there are a few conditions going on here from the Clebsch-Gordon coefficients. In order for you to be able to couple angular momentum A and B to angular momentum C, there's a condition on that, right? The condition has a name. We'll give you a hint. The triangle inequality, okay. Basically, the three vectors have to be able to make the sides of a triangle. Since we're over time, I'm allowed to write in the hidden area, right? So A, B, and C, which basically means A minus B is less than or equal to C is less than or equal to A plus B. And then for the angular momentum projection components, what has to be true?
The sum must be equal to that.
Yes. This is a projection along an axis. Take two vectors, project them along the axis. Their sum vectors projection has to be the sum of the projections. So we'll have alpha plus beta equals gamma. So even though I've written this as a double sum, when we decided what gamma is, you run over the values of alpha and the value of beta follows. So I could write this out, but I'm told that I have to stop 2 minutes ago, right? Or should I write out the alpha plus alpha?
You could say that most coefficients are equal to 0.
Most coefficients are equal to 0.
Yes. For instance, 2 to 6 is
Oh, I see, yes. all forbidden coefficients are equal to
Yes.
0, yes. Actually, there's a countably infinite number of both 0 and non-zero, so it's equal sized infinities. If you have a central force problem, that was one where the potential only depended on the radial coordinate r. And if you solve for the wave function, the first thing you did, I brought the energy over to the left-hand side here for some reason. Okay, the first thing you did was you realized that if you try out a solution, r theta phi, being a radial wave function, and it was convenient to get the radial equation to come out nice to divide out a factor of r, that got some terms to go away. You had a radial wave function times an angular wave function, and this angular wave function did not at all depend on your actual radial potential. It was, no matter what your radial potential was, your angular equation was the same, and it gave you the spherical harmonics as your solution. So the u function here will depend on the angular momentum quantum numbers, and also will have some sort of radial node counting quantum number. And this solves the radial equation, which I'm going to write out, since we'll see that in 5 dimensions we have basically exactly the same radial equation. The only thing that makes it not exactly the same is that it's different. This thing has to equal and then the YLMs came from an angular equation, and the important thing was that they're an SO3 angular momentum eigenstate. That'll be important because we'll see something very analogous when we get to 5 dimensions, and this eigenstate of L squared is what gave us the L plus 1 as our separation constant. Now, okay, that was 3 dimensions. Let's look at 5 dimensions. And my microphone is dangling at my feet. I don't know how long it's been doing that. But if you want to listen to my footsteps again.
Maybe you should reattach it.
Or speak through my feet, one or the other. I'll just talk down to my feet. Can you hear me okay? So, 5 dimensions. The analogous situation is, well, we're already using Laplacian for our kinetic operator, and now what if we have a potential that's a function of beta only? The harmonic oscillator in 5 dimensions, for instance, will be beta squared potential. It's E and L. Our wave functions are functions of beta, gamma, Euler. We're asking that to equal 0. We can do a separation of variables the same way. Remember though, in our kinetic energy operator, we had some different derivative powers of beta floating around from what we had in the 3-dimensional case, powers of r squared. So it turns out that we'll want to divide out a beta squared here from our radial function. So again, we'll have a node quantum number, the n. And then this V here is the SO5, it's often called the seniority quantum number, but it's basically the angular momentum quantum number for rotations in 5 dimensions. Not to be confused with the L quantum number, which is a 3-dimensional rotation quantum number. And then, so our remaining angular wave function, I'm going to call that capital psi, will be a function only of the angular variables, which are gamma and the Euler angles. And just like before, we had L equals 0, 1, 2, and so on. Here, V will equal 0, 1, 2, and so on. This U and V of beta solves a radial equation, which is in fact, in n dimensions, you get basically the same style of radial equation. All that changes, the one little change, is you get an offset. Instead of L plus 1, we'll have V plus 1, V plus 2. Here in 5 dimensions, those constants will keep changing as we go to different numbers of dimensions. Minus E and V, U and V of beta. The angular wave, but this is beautiful because we have the exact same radial equation. Suppose you plugged in L equals 1 in 3 dimensions. That's the same effect as plugging in V equals 0 in 5 dimensions. Exact same radial equation. You can just pick up your solutions for your quantum mechanics class. Every time you see an L, replace it by a V plus or minus 1. Just make sure you get straight which direction to go, which is, you have to sit down and think about it for a moment, and you have your radial solutions. Angular solution, sorry, it's set equal to 0. Okay, so the angular solution is the SO5 Casimir operator, SO5 angular momentum eigenstate, which basically means, let's refresh our memory what that was. That means those are the eigenstates of this ugly beast in parentheses. The good news is you only have to basically generate them once and you're all set. Just like in practice, spherical harmonics, it doesn't matter how ugly they are because you look that up in a table, right? Same basic idea here. Yes?
So, with this analogy between L and V,
Yeah.
3-dimensional 5
Yeah.
is there an equivalent of like a 5-dimensional angular momentum projection quantum number?
There are 2 ways of looking at that. So, even though SU2 or SO3 is always the wonderful first analogy for understanding higher groups, it's often not quite clear how the things will generalize until you see exactly how they generalize. So in fact, there are, if you look at SO5 by itself, there are 2 so-called weight operators. So it'd be like there are 2 different projection operators. The way things are normally treated instead, though, the basic issue is, in 3 dimensions, an SO3 representation is pretty straightforward. If you have the representation L, you'll have M equals minus L up to plus L, and so you can label all the states just with one projection quantum number. Turns out when you go to SO4, 4 dimensions, you can play the same game, but you will have a grid of states, and you will have 2 projection quantum numbers, let's call them Mx and My, and you can again label all your states with those 2 projection quantum numbers. When you go to SO5, things become a little bit ugly. It turns out you still just have those 2 projection quantum numbers, Mx and My, and you start getting multiple states at the same location. So you need some extra missing index or multiplicity index. Okay. So the end is these spherical harmonics. In fact, that's actually a great question because the other way you can group these states, this would be sort of the direct approach, saying there's SO5 and that's all there is. But we're interested in having good rotational properties, so we actually want to make use of the fact that SO5 has SO3 as a subgroup, and that means that we actually take different linear combinations of states, which don't necessarily have mx and my even as good quantum numbers. And we will label our states by V, alpha, which is this multiplicity index, the L of the state, so the SO3 angular momentum, and the M. And we will get a bunch of states, lots of magic goes on, but you can construct these functions. Again, these are of gamma and the oil. Those components equal to 0. And I sort of hand waved it beforehand, saying it's a matter of Legendre polynomials. Remember, the y plus or minus 1s are basically the Legendre, so 2 plus or minus 1s are basically the Legendre polynomials 2, 1, and then an e to the I plus or minus 1 times phi. So what we're after is this Legendre polynomial of cosine theta. So let's see what those different Legendre polynomials do for us. If we plot the Legendre polynomial P20 as a function of theta, that is this first plot. So we'll see that it adds at theta equals to 0, subtracts at theta equals to pi over 2, and adds again at theta equals minus pi, theta equals pi rather. Sorry, theta is coming down like this. So that maintains the z-axis as a symmetry axis. All is good, or potentially good. Let's look at Pu21 though. That would be our next plot. If we start with a sphere, we start by adding on 0 at the pole. Then at pi over 4, we're adding. We add on 0 at the equator. We're subtracting at 3 pi over 4, and by the time we get to pi, we're back to 0. So notice what that's doing. That's trying to give us a shape pointing out this way, which is very much not aligned with the axis we want things to be aligned with. Let us now look at the final one, which is P22. P22 is looking okay. We start by adding 0 at the pole, we add at the equator, and then we get to 0 at the pole again, so let's draw that on both sides. So that looks like it's along the axes. So that could be symmetric along the x or y axis. This pen writes in a combination of red and black. That's amazing. Wow. Okay, so that is okay if that happens to be along the correct direction in the equator, the x direction or the y direction. But what if it's going out midway between those two directions? That will all depend on the e to the I plus or minus 2 phi factors. You need the correct linear combination to give you stretching along the x or y axis, not in between, and that's where the condition of reality comes in for the A2 plus or minus 2 real. We'd have to play with a little bit of trig with those e to the I 2 phi's to be sure of that. So I think that's probably a little bit more of an explanation than we had before. All right, so we will now try to cover the rest of physics in 1.5 hours. And the backup on all this is I figured I'd actually write down a bibliographical information for a very meticulous step-by-step, has all the details review of everything here. So if you do need to go back and work on this type of stuff, I very much recommend that as one of the best starting points. So there's some.
One question. Are you gonna put this all notes in websites?
I have had a request for that. I will try to write something up neatly. However, since I can only work at finite speed, it would not be for this afternoon's this exercise session, but you actually don't need terribly much of this for the exercise session, I can point out. If there are any,
No, so but this will because writing down all these things and understanding as well that is very difficult for
yeah.
at least me for. So if you put that things in the website, then it will be okay because we just
Okay.
try to understand.
Okay. Okay. So there are some, let's see, all right, so let's go back to the image we have of what these coordinates mean. We've said that beta and gamma describe a given shape, but there's actually some funny business going on with these coordinates. Different values of beta and gamma, when you plug in what they mean in terms of the spherical harmonics, draw the shape that comes out, will give us the same shape, but just pointing in a different direction. Which isn't so nice because that's what the Euler angles are supposed to do. The Euler angles are supposed to rotate us to a different direction. The reason for this is that we have said, oh, here's this magical approach that aligns our shape along the intrinsic axes, but we never said which should be the long axis, which should be the intermediate length axis, which should be the short axis. There's an ambiguity there. There's actually an ambiguity both in the labeling of our axes and also in which direction they point. There are 48 different transformations you could do on our axes and still have a valid set of intrinsic axes. So we have to now, on the other hand, if we're defining a Hamiltonian, there are certain invariance properties we want. When we say that we all know that our Hamiltonian should be rotationally invariant, we're going to be defining a Hamiltonian as a function of this deformation tensor, so basically the shape of the nucleus. Certainly, the nucleus pointing this way shouldn't have a different energy from the same nucleus pointing this way. So it's natural to say, okay, it should be a rotational scalar. The Hamiltonian should be. But there has to be more than that, because now it turns out we can have, for instance, the exact same Euler angles, but shuffle around beta and shuffle around gamma, and we'll get the same shape, but pointing along a perpendicular axis. So what we needed was, moreover, a Hamiltonian that's invariant under any of these switching. Switching the names of the axes should not affect the energy of your system is another way of looking at it. I'm realizing now that I should have made some pretty pictures showing different gammas giving the same shape, but pointing different ways. Oh well. So I want to just do this very quickly, so to the point, though, that you get the basic take-home that will come out of it, which is, okay, there's the octahedral group is the symmetry group. You realize it's the same symmetry as an octahedron. There are basically 3 axes for an octahedron. An octahedron is invariant if you flip the direction of either of those axes, or if you rotate one of that set of axes. So permutations and flippings of the 3 coordinate axes are the same as the octahedron, so okay, we have a fancy name for it. The important thing is that you can generate all those transformations from a few basic transformations. Okay, identity transformation, that's trivial. 3 rotations, and then inversion in space. So these are the Euler angles. So like, let's see, this last rotation is the one that permutes the 1, 2, 3 axes into the 2, 3, 1 axes. I can't pretend to quite do it. This is a rotation around the z-axis followed by the y-axis. This is a rotation of pi over 2 around the z-axis. And the thing is, these are what those rotations do to the axis labels, but we're interested then in translating that into what those rotations do to the intrinsic coordinates beta and gamma. There's algebra that comes in here, which is not in my lecture notes. It's long algebra. But the point is, this first rotation actually leaves beta and gamma unchanged. The second rotation flips gamma to minus gamma. So our Hamiltonian will have to be symmetric. If we flip gamma to minus gamma, we actually have not changed the shape of the nucleus. Similarly, if we subtract 2 pi over 3 from gamma, we have not changed the shape of the nucleus. So our Hamiltonian should again not change its value. we can sketch what this means in the polar plane. When you have a visual picture of this, it'll be a lot easier. So this means that 2 pi over 3 is a very special angle. So that's 60 degrees in common parlance. So anytime, if you take, say, the potential here, so if so this is our A0 axis, this is our A2 axis, our deformation coordinates. We're all happy dealing with particles moving in abstract five-dimensional spaces, right? Natural. So we now, the potential has to be the same at that point, rotated by 2 pi over 3. It also has to be the same when we go to, so when we take gamma to minus gamma. And again, we can repeat these as many times as we want. So basically, we will have, where's the next axis like this? So again, 2 pi over 3, 2 pi over 3. You've all played Trivial Pursuit at some point? Yeah, so that's the easy way to remember this, these axes. Is that, who has played? Who knows Trivial Pursuit? Who does not know Trivial Pursuit? It's okay. You're probably a better person if you don't know Trivial Pursuit. Okay, it's a board game where you have little pie-shaped things with 6 little, and you have to, by answering trivia questions correctly, you basically get different colored wedges that you fill those in with. Okay, so it's just like the Bohr Hamiltonian. It's easy. Okay, so, right, so we have this symmetry. Any set of points like this, Hamiltonian has to have the same values. Okay. So, what does that mean for us? We're talking about Hamiltonians. We've been looking at the potential now. We've figured out the symmetry conditions it has to satisfy. But we're missing a very important ingredient. We still need a kinetic energy operator for our Hamiltonian.
So
yes.
can you go over just your thoughts? So you say your Bohr Hamiltonian should be invariant according to these rotations.
Exactly.
So it means that we can map all these shapes just going from 0 to 60 degrees.
Exactly.
But what was your step to say that the Bohr Hamiltonian should be invariant against those rotations?
Because if you go beyond, it's a claim basically.
A claim?
These rotations are the ones which just rotate these axes onto themselves with different labelings.
So you can use these D functions to do these things, not
yes.
using. Yeah.
That's right. D functions on the spherical harmonics would be one way at least of doing it. It's ultimately coming out of the spherical harmonic properties, and you can rotate. Yeah, do a D function to rotate the spherical harmonics, and you would ultimately get this. Gap in logic, I know. Yes. Or gap in derivation, at least. Okay. So the moral was V of alpha should be a V of beta gamma to be invariant under rotations in general, independent of Euler angles, and then it should be symmetric under these operations, gamma to minus gamma, and gamma to gamma plus 3 pi, 2 pi over plus whatever, so ultimately, to 2 pi over 3. Okay, now, for our kinetic energy operator, here's the fun part. We have a very large infinity of possible operators we could choose, right? This is not a real particle moving in Cartesian 3-dimensional space. This is some effective Hamiltonian, which we're hoping somehow comes out of the microscopy for the nucleus. And the question is, does it even have a Schrodinger-like equation governing it? There are derivation modes, there are various approaches that can give you something that looks sort of like a Schrodinger equation with a lot of flexibility in the kinetic energy operator. We will basically only discuss today the leading order term, the simplest one you could imagine, which is say, let's pretend this is what Bohr and Modelson originally did. suppose this is a Schrodinger equation, and let's look back. We have a set of Cartesian coordinates here, real Cartesian coordinates. We can let our Hamiltonian be the good old Laplacian. Okay, 5-dimensional space, but still the Laplacian.
Could
Yes.
you explain once more maybe what the effective Hamiltonian is, or what do you mean by effective Hamiltonian?
I mean, let's say a Hamiltonian for these degrees of freedom, which we've decided are the degrees of freedom of our nucleus. So we've you know, two parts of the model. We have a space and the Hamiltonian. Our space here, we said, let's say that we have these deformation coordinates, and we'll take wave functions on these deformation coordinates. We then need a Hamiltonian for that, and that's where our creativity starts to come in. I mean, historically, this was very much at the level of, okay, in the 1940s and 50s, there was the idea that the nucleus could be treated for certain purposes, like for fission, as a liquid drop. And you could have a classical Hamiltonian for a liquid drop described in terms of these 5 deformation coordinates. And you can follow the quantization procedures for a classical Hamiltonian, and you'll get a quantum Hamiltonian that looks something like a Schrodinger equation Hamiltonian. That is purely at a phenomenological, let's try and see if it works level. Then there are modern approaches like time-dependent Hartree Fock, and then quantizing that, and then
So you mean-
yeah.
So you mean you add some constraints to the Hamiltonian?
Right. Right.
Like, I mean the deformation one, yes? Like, and in order to get some Ruthian or some constraint Hamiltonian, yes? You mean by this effective Hamiltonian, you mean the Hamiltonian with the adding term, like the constant of deformation here?
I'm not 100% sure I understand what you're saying, so let me see if I can say it the way I think, and you'll tell me if it's the same thing. We will be taking some constrained form for the Hamiltonian, like saying, okay, this is the family of potential functions. Well, you know, ideally, we would just take one of these microscopic approaches and get a Hamiltonian handed to us out of that. And there's continuing effort on that, but it's certainly not at the level of being perfect that we can just do that. Whereas today we're viewing this at the level of, okay, let's treat this phenomenologically, but all the machinery we build up is stuff that if someone handed you a Hamiltonian microscopically, you could then use it. You've built up an intuition doing this. I think I got time to input. Okay. Okay. So the idea then was start from the Laplacian in 5 dimensions, but that might not be the form we ultimately write it in. So that's saying Hamiltonian is minus h bar squared over 2d, where b is playing the role of a mass in the Schrodinger equation, but its connection to actual masses is a pretty distant one. Kinetic u beta gamma, and it's like our v of beta gamma. So what is this Laplacian? We're going to fill in a few steps here, and we're going to again have some leaps of derivation. It is immediately intuitive to the most casual observer that this, after 12 pages of algebra, that this follows equals minus 2, because we're using k for that. K equals minus, no, I don't know what it is we're using. Yeah, this was a Cartesian coordinate, so yeah, I equals minus 2 to 2, derivative with respect to xi, second derivative. So this is Laplacian on R5. Then this could be rewritten in terms of the complex coordinates. So we're going in order basically from least scary to scariest looking. So we've thrown in some complex conjugates, we're getting a little bit scarier. And then it is immediately obvious, yes. Okay, we have our final form, which is going to, there's not enough room to write it here. So, okay, I'm going to say something in a moment then that will make this look a little bit less crazy. So this is, if we rewrite this in terms of the Bohr values, beta and gamma, We then have plus 1 over beta squared. This is on some slide somewhere, so actually we can just go to that. So I'm writing down this thing on the bottom here. Okay, so let's just do this as dot, dot, dot. You have it on the slide here. I've color-coded blue, everything that depends on beta. Red is, can you more or less see that? I'm not sure I really want to get into turning the lights on and off. Red depends on gamma. Green depends on the intrinsic frame angular momentum components. There is one important thing to notice, though. This thing in parentheses, that big, horrible, awful operator, is minus times something we're going to call lambda squared. This is the SO5 angular momentum. It's the 5-dimensional analog of the L squared operator. The reason I point this out is we'll have need for it again, but also, yeah, but this should actually look somewhat familiar to you when in retrospect. We've done something very similar. Remember, in 3 dimensions, you had the Laplacian, which looked nice and simple, derivative with respect to x squared, y squared, z squared. In Cartesian coordinates, then you did that messy thing, maybe Jackson electrodynamics, of converting it to spherical coordinates, and you got that the Laplacian was equal to 1 over r squared, derivative with respect to r squared, d over dr. That's starting to look suspiciously like this. It's just that the power's gone up from 2 to 4. As you might expect, the dimensions go up. Maybe some of your powers will change. Plus 1 over r squared, directly analogous to the 1 over beta squared. I guess there's probably, do I have a minus sign missing? I may have a minus sign coming for fun. I'm not sure what's going on. Okay, 1 over sine of theta, derivative with respect to theta, sine theta, d over d theta, which is very much in the form of gamma here, which is sort of the first angle we've taken out of our set of angles, and then plus 1 over sine squared theta, derivative with respect to phi squared. And in 3 dimensions, this was just the negative of the L squared operator, our squared angular momentum, so that was the SO3 angular momentum. Important to notice, because a lot of that structure will carry, a lot of the things that we did in 3 dimensions, like doing central force problems, where we found that the angular wave function was a spherical harmonic, can be repeated in 5 dimensions. Any questions at this point? Obviously, we have not derived this, but we're just playing it. Yes?
What is that at the bottom there?
On the screen?
Instead of the angular momentum term on the right, is it a 2/3 pi gamma?
Yes, it is. And you will be getting the slides. Anything else? All right. So I'm trying to think to prioritize what are the most interesting things to cover. The other thing we stated, so I'll abbreviate something a little. We also said once we have our space and our Hamiltonian, we also need our transition operators. Here again, it's a lot of, you need to know the microscopic underpinning to really know what the correct transition operator is. You can propose something based on what you expect in the leading order, or you can put in some hypotheses, like say, suppose this is a uniformly charged liquid drop, then we can calculate what the electric quadrupole tensor is and write down that operator. In fact, that's the approach that is usually taken. So the idea is, okay, we have to write our operators, The only one that I'm going to write down right now is our electric quadrupole operator. There can be some very general form for it. So Q is a spherical tensor operator of rank 2. It will be, in general, some function of beta and gamma times alpha 2 mu, plus another function of beta and gamma times alpha 2 cross alpha 2 coupled to 2, and so on. But you'll often see the classic form. Basically, if you take a uniformly charged liquid drop, then the quadrupole tensor depends on the number of protons, the size of the nucleus, and then you can look at the surface deformation, see what that gives you for the charge quadrupole moment, and you'll get something that's alpha 2 mu plus some higher order terms. So basically, our coordinate vector also doubles as our quadrupole operator. That's sort of similar to one-dimensional problems where the coordinate x also serves as your dipole operator. Okay. Now, there are a few special cases that we should look at, and then I want to discuss in the time available the general numerical solution. So the basic cases where we can come up with some form of solution without going all the way. Actually, we're about to answer one of the questions that came up earlier about the coefficients in a rotor, is if you have what would be called an adiabatic rotation. This means a large separation in energy scale between the rotational degrees of freedom, those will be low energy, and then the vibrational degrees of freedom at high energy. Another way of looking at that is that the vibrations are small compared to the deformation. So schematically, if you had a potential, you would expect this type of situation. So here's our V of beta gamma, A0, A2. Generically, so you could have some triaxial shape, and then suppose you have a very deep, very steep potential. I'm trying to draw an oscillator. Every potential near its minimum looks like a harmonic oscillator. Those contours will close. You could imagine that the nucleus is like a rigid rotor with this particular deformation, but then is able to undergo small oscillations around that shape. This would be a generic case. Now, in fact, the case that you've seen so far is the axial rotor. So I'm actually going to skip the generic case since one never actually encounters that in practice. Here, you would have an equilibrium that's at gamma equals to 0, and then small oscillations around that. Again, what I'm trying to draw here are contours of the potential and the plane. People comfortable picture. You're all comfortable with contour plots, right? I've seen people get very confused with these. That's why I'm sort of asking and looking critically. This isn't meant to mean vibrations. That's meant to represent contours of the potential. Okay. So the basic thing we would do, maybe it is easier to look first at the triax, the generic case. There's something ugly. So if we look at this Hamiltonian, generically, you'd say, okay, well, we can't throw away the derivatives with respect to beta But if beta is approximately a constant, there will be a domain where this thing basically looks like the second derivative with beta, and there will be some higher order correction terms. Delta squared, so del squared would basically be the second derivative with respect to beta. And then here, this beta could be replaced by beta, so let's call these coordinates beta naught and gamma naught would be the equilibrium position. So for the gamma degree of freedom, we'd be able to approximate things basically in leading order, then there would be some extra terms in the Taylor series. But a constant, and we'd just be left with 1 over beta naught squared, second derivative with respect to gamma. And then in the rotational kinetic energy here, we would have, notice that these terms on the bottom basically function to 4, so now you can see 4b times sine squared gamma minus whatever is our moment of inertia. So moments of inertia here, let's write that down, are 4b beta naught sine squared gamma naught minus 2 pi k over 3. Okay, it's an ugly expression, but we have to live with it. But it would be nice if I used the same subscript on both sides, wouldn't it be? Okay, what letter are we using here? We're using capital, let's call that K. And the K there. So we have minus sum K equals 1 to 3 of this now static value 1 over K L at prime squared K, where this is now a constant. And this would be nice. This basically, notice what we have here. We have a separable Hamiltonian. And so in the kinetic energy separates into a purely beta part, purely gamma part, and a purely Euler angles part. Life would be great. We'd say, our potential also separates V of beta gamma is basically a 1/2 C beta beta. I mean, the curvature in the beta direction, beta minus beta naught squared. Think of a paraboloid sitting right here. They'll have curvature, different curvatures potentially in the 2 directions. You could have a cross term, but our symmetries, I think, get rid of that. Plus 1/2 C gamma gamma, gamma minus gamma naught squared. Beautifully separable Hamiltonian. So our Hamiltonian is a rotor plus a Hamiltonian for the beta direction, plus a Hamiltonian for the gamma variable. Both of these are just simple harmonic oscillator Hamiltonians with some subtleties, but okay. So the energies would be rotational energies, going as L plus 1, plus vibrational energies in the beta direction, which is the n beta that we had a question about earlier, plus in the gamma direction. Where these h bar omegas just come from the mass parameters, where is the mass parameter B and the curvature. So once we know the curvature, once we know the mass parameter, we could estimate the vibrational energies. Frequency is curvature divided by mass. And then for h bar omega gamma, we have to remember that there's this extra beta naught factor sitting there acting like a mass, so we would have C gamma gamma over beta or beta naught squared B. Now there's one fatal flaw in what I've just done. If we go to the axial motor case, any idea of what goes wrong? Not completely obvious, I guess, until you try to plug in.
No effective mass in the direction.
Yeah, so basically if we plug in 0 here, we'll end up with, for the k equals 0 axis, if we plug in 0 here, we'll get sine squared 0, which is 0 sitting in our denominator, which not a nice thing
That-
to be doing.
Well, we cannot rotate around axis of symmetry.
Well, this is actually the intrinsic axis. Yeah, okay, exactly, yeah. So it's, yes, it's related to the idea of yes. that
It's
it- yeah.
literal.
Yeah. Yeah.
So with your generic V here,
Yeah.
you have the coordinates beta squared, beta cubed, cosine, gamma. So it looks like cosine is going to be decently represented by our harmonic oscillator because you're not going to have a cubic value. But this beta cubed here maybe means it's less good approximation or in the beta direction. So if you
Well, but you're still expanding around the minimum. So
Yeah.
it's not, it'll be beta minus beta naught, that's the quarter.
right. Well, I guess my major question is why have these variables been selected out among them?
Oh, over here, you mean?
Yeah.
Oh, yeah, and I'm not actually a fan of writing it that way, so I apologize. So these are combinations that, so basically, yeah, so if we look back at what our symmetry constraints were, are Hamiltonians allowed to, maybe a better way of putting this, much better and preferred, this has historical origins in the geometric collective model, basically. The key thing is that we can depend on beta, and we need a function of gamma that has those trivial pursuit symmetry properties, and it's cosine 3 gamma, which has those properties. So it's really, we need a function of beta and cosine 3 gamma. And as we'll see, actually, technically, that's included here because you can take square root of beta squared and then divide it out from beta cubed. The historical reason here was, that will come naturally in a few minutes. Let us, I'm just looking at time. Let us come back to what was going on here. So for an axial rotor, we have to fix this up.
Excuse me.
Yeah.
So the first line, the Laplacian, you approximate to the equation, the first line.
Oh yes.
So
Yes.
what did you do actually? What is the approximation?
The approximation is basically taking these things, which are variables, and in places where we can, we're expanding them out as beta equals beta naught plus some small difference. Gamma is gamma naught plus some small difference, and then doing a Taylor expansion of that. Yes. So for an axial rotor, J3 is equal, sorry, the moment of inertia is equal to 0, and as was pointed out, that's because basically we have a shape that's symmetric around the 3-axis, and there cannot be rotations around the 3-axis.
So put the prime in the J.
Except that the moment of inertia is always defined around the intrinsic axes.
Okay.
Yeah. Yeah, it would be clean in some way, but nobody does it because that's only axis that makes sense. Otherwise, we have a generic tensor instead of just 3 moments of inertia. Okay. So gamma naught equals 0. Need a different expansion. And I am seriously tempted, should I actually bother writing it out? Is it worth writing it out? In the interest of time, maybe I'll just skip to the, no, that's silly. No, let's just dot, dot, dot. I can write it up. See, that's, once you ask me to put my notes on the web, there's this wonderful excuse for me to skip things and say that I'll put the notes on the web. Okay, so the short version is that doesn't make sense. All right, if I skip some stuff later, that's fine. We can skip gamma independent potentials or something like that. They're overrated. Okay. The reason I hesitate is because obviously it's a big mess to actually derive all this. So just take away the general picture here, which is that we get some different operators. We again have a T beta. We now have a T gamma that depends on the angular momentum projection along that axis. So it will depend on K. Our separation of variables will get messier, and then we're again left with some difference of angular momentum vectors, components rather, for our rotational kinetic energy. But we will still get a separation of variables. The bottom line is we still get a separation of variables, but where the K quantum number starts coming in, so we still have separation. And our energies will depend on K and L, but also the number of oscillator quanta from the beta part of the Hamiltonian and the gamma part of the Hamiltonian. And those are those numbers that came in the level scheme earlier. So here, before I even write the energies, let's stress N beta, N gamma, K, L, M. I'm using capital N's because there's some ambiguity. Sometimes people... So here's a piece of trivia for you. This oscillator equation is actually the radial equation for a two-dimensional harmonic oscillator. This is a bit bizarre, but the gamma vibrations are actually vibrations in some two-dimensional space. If that means anything to you, then explain it to me, please. I can't picture it. Okay, L plus 1 minus K squared. So is our rotational energy. So if you ever see mysterious formulas where the rotational energy has a K squared subtracted off, you know that comes from this way of trying to maneuver the separation of variables. N beta plus a half h bar omega beta, that at least is straightforward, plus N gamma plus 1 h bar omega gamma. So that gives you the basic picture. There are some selection rules, though, that the K quantum number can go from 2 times N gamma down in steps of 4. So the way of picturing this is actually what you'd expect if the gamma phonon had plus or minus 2 units of projection along the axis. So imagine how this would work. This is, I believe you had a slide like this from Rick, actually. This becomes much clearer if we have a level scheme drawn. So start off with our ground state, which will generally be K equals to 0. This has, so angular momentum will be 0, 2, 4, and so on. So the point here is that N gamma is equal to 0, and also N beta equals 0. When N gamma is equal to 0, what are the possible K values? They start at 0 and go downward to 0, so it can only have K equals 0. Let's suppose we add in N gamma equals 1, though, still with N beta equals to 0. Our K values will be 2 times 1 is 2, downward in steps of 4, so if any more K values. Sounds either means it's obvious or I've completely dazed you. So we will have K equals 2. That will then go into 2, 3, and 4, and so on. This energy difference is basically h bar omega gamma with a little subtraction due to this. Okay. Okay. Now if we go to n gamma equals 2, so here's the way of thinking about this. If gamma is the Rick, you don't have the empty coffee cup with you.
No, because we're not allowed to have drinks in here.
Oh,
I
okay.
didn't discover that until after I.
This can only be illustrated with Rick is in the room using an empty coffee cup.
You were doing folded paper.
Yeah, yeah. Yeah, Mark, here.
You can take this.
Oh, perfect. Just imagine virtual coffee in here. Okay. So, with our Legendre polynomial before, if this was our z-axis, we saw that the P2, the gamma degree of freedom, would cause bulges around the equator. Now, what was the point of all that? Yeah, okay. So, the point is that is also, a superposition of those is this rotational standing wave going around the equator. So you can picture this as actually carrying angular momentum around the equator. If it carries, so that's basically a projection on the equator, some amount of angular momentum, and we actually saw that was an even I plus or minus 2 phi, so it would be 2 units of angular momentum around the equator, so that would give us a projection of 2 or minus 2, but we actually saw rotational wave functions are symmetrized plus or minus k, so it doesn't matter which we use. Now let's say we add another quantum though, n gamma equals 2, then our rule was that k could equal 2 times that, so 4, or go down in steps of 2, that would give us 0. So that, again, sort of makes sense. If we have plus 2 units from the first, we could then either have plus 2 from the second phonon, or minus 2, so that would either get us up to 4 or back down to 0 for the angular momentum of this standing wave around the equatorial axis. In fact, that reminds me, coffee cups aside, there is a beautiful picture of what's going on. So this is like what we were sketching before, where we had our spheres and then added on the Legendre polynomials. Well, what if we start with something that's already elongated along the z-axis and then add on? Remember, our first Legendre polynomial would add more at the poles and subtract in on the sides. So if we have a vibration in the beta degree of freedom, that's adding basically y to 0 on. That will be classically a motion of elongating and contracting along the poles. So picture an extension like this, but with time oscillation, that means that you get a minus sign a little bit later, so it would be subtracting at the ends and adding on the sides, and so on, and then oscillating back and forth with time. For the y to 2, we start with the long shape, so I should do that now. I know this is off the edge, sorry. That means I have to erase some. Well, you have that version of forward. Maybe this will barely squeeze in on the edge. This will be an experiment to see if it shows up on the video. So then we have a shape that's elongated this way, but we start adding on one side, picture Saturn's ring, but sort of deformed, starting adding on the sides and contracting on the other sides, and then it alternates. So, I don't know, yeah, I can't come up with the analogy there. So that's exactly what we're illustrating here. So that shows oscillations out on the sides or back in. Now, the remaining Legendre polynomial, we saw would add lumps at the 45-degree angles. So let's see what happens if you take an elongated shape, start adding nothing at the end, but positive here, negative here, positive here, negative there. What's happened to our shape? It started rotating. So this is actually a spurious mode. That leading order, the shape hasn't changed. It's just the whole thing has started rotating, which is why we actually don't have a vibration corresponding to that. That actually gets lumped into what's going on with our Euler angles and is part of the rotational motion. Thank you.
with all of these vibrations and
Yeah.
rotations, is the volume always conserved?
There are two answers to that. In the small oscillation approximation, the answer is, so my recollection is that it's only conserved in the limit of small oscillations. If you went to larger oscillations, you would actually include a monofold term correcting. So you'd have to, instead of having a 1, your 1 would have to not be. Your 1 would have to become a 1 plus alpha 0, 0, basically, which would have to change to compensate.
But is this something that the physics requires? Is that the volume is conserved, or should the physics allow this thing to kind of expand?
I don't think we know the physics enough to answer. There's very much a claim that this whole idea of the quadrupole coordinates representing the shape. So, I mean, if we're saying that the shape here is a uniform filled liquid drop, that's not the situation. Yes. You can argue that the quadrupole components should be the quadrupole tensor derived microscopically and have nothing to do with the shape, even in which case there's no volume to conserve per se. You can argue that there are mathematical artifacts